Alrighty. Okay. Yeah, I'll go over all the tasks. Okay. So here's a sign-in sheet for whoever has not signed in yet. So please do. And then, yeah, in a minute we'll go. All right, okay. So this is task one basically. So, it had to be on the 5 volt. The picture is a little bit bad here, but it is on the 5 volt, both terminals, right? Oh, let me go back. And then the blue wire is basically the positive here, and the white wire, no, I actually have it wrong. The wire is connected to the yeah, on the description I have it wrong here, but I'll fix it. But yeah, okay, so the positive one is the blue wire, the negative one is the white wire. I really recommend you guys using jumper wires than just plugging things into the circuit. Jumper wires gives you this option to kind of understand how your circuit is actually completing. So if you have a closed loop or anything, it would just help you a lot. Anybody has any questions? Any questions anybody has about task one? Okay, and here's the side view. Basically, again, the 5 volt should be on the 5 volt. If you had it on 3.3, it wouldn't have probably just turned on. It would have been really dimmed. So yeah, and again, what blue wire is on the positive rail, the white one is on the negative rail, and here, basically, the circuit is going to complete. If you follow my cursor, okay. And this is the side view. Any questions before I continue?
So Sina, I had a question.
Yeah.
In this case, we consider the light as a resistor, right?
Hmm?
And you said yes?
What was the question again? I'm sorry.
In this case, we consider the light also as a resistor, right?
No. So, that one is for tasks two, which I'm gonna
Oh,
go right now.
okay. Because I was
Okay.
gonna say like if we want to calculate like how we can
Yeah.
calculate
Yeah.
resistance.
Yeah. Yeah. Okay. So, yeah, we'll go over it right now. So, anybody
Yes.
has a question about task one?
Yeah, Sina, can I interrupt just for a second?
Yeah.
Tal and Polos, I sent you a private message in the chat. Can you please respond? Thank you.
Okay. Should I continue, Wes? Okay. So, all right. So, task two. Anybody has any idea what was task two about that they want to talk about it? Just open your mic, send in the chat. Just go ahead. Someone.
I think just understanding that current is like the same, like in a series circuit.
Right. And then what was anything else about the task two? What was the question asking us?
Like if the lights are the same, right? Like not as dim and stuff like that. When adding like 4 or 5 LEDs.
Kind of close, but I need a better answer.
Is it basically showing like the more lights you put, the dimmer it'll get because they act as resistors?
Kinda, but it's still not correct.
Gotcha.
Was it like how to make all three lights light up without changing anything about the circuit? Like, I don't know. I was thinking like voltage divider, but I don't know if that's the right thing.
That
Yeah.
that is kind of the right mindset too. But anybody has a better answer?
It's like we can connect up to how many lights in series and make them like kind of turn on.
Right. So the problem was all about we had one, what is it called, LED in a circuit, it would light up. When we add the second one, it would still light up both of them. But when we add the third one in series, it stopped lighting up. It would just be really dim for some people, right? So then the question was like, I measured them with the, what is it called, ammeter. So I was like, oh, first is about 15, then it's about 1 to 3 milliamps, right? And then like when the third one just added is 24 microamps, right? So what is the, if we count them as resistors, what is the what's gonna be the resistance, right? So what I was really gonna talk about at first is that we need to, before attempting any type of problems, right, we need to sit back and just read the question well, right? What is the question is telling us? What is the information we're getting, right? So what is the first observation we can take from the question? What is the first observation we can take? Anybody?
There's internal resistor in resistance.
Not really, because like if you Google or like if you know, LEDs don't have really internal resistance.
Is it like no matter what, like when we change the third light, is it still like not turning on? Like a first observation.
Yeah, something like that. But if you pay attention, right, the first thing that the problem is telling us is like the current is dropping exponentially, right, as we add more resistors, right? At first it's 15 milliamps, then it's about 1 to 3 milliamps, then it's about 24 microamps, right? So we see that the pattern is not linear, right? So when the pattern is not linear, right, we can't really come up with exact resistance of a LED, right? But we can solve it based on how the circuit is behaving. So we can kind of find out what is true about it. But we can't really talk about, oh, let's say like the yellow LED has this much amount of ohms, right? This is how much has resistance. Anybody has any question about it? Any questions? Any questions? We continue. Okay. I will get to that. So you had to have the, what is it called, 220 ohm resistor anyways in your circuit when you were adding the resistors in series, right? But then when your kind of, what is it called, like your ampere is dropping exponentially, right? That means your resistance, your total resistance in the circuit is actually increasing a lot, right? So later I'm gonna show the answer and you're gonna see it doesn't really matter if you count it in or no, because the total resistance is actually high a lot. That's where you're getting a really low ampere, if that makes sense, right? So then what is the next step that we always need to take into just solving another problem, like any problem, is to just break it down to smaller pieces, right? Oh, okay. I added 2 resistor, it worked, the third one didn't work. Question is giving us 3 variables in amps, right? So these are all the smaller pieces that you need to put together to kind of understand the problem, right? And then sometimes also, just as a tip, just sometimes you can't really solve a problem, just stay persistent and just continue solving it till you get the answer, right? So just some tips before we continue doing the problem. All right. So I saw a lot of people having them in parallel. So that's how your circuit should look like, right? So again, your blue one is the negative, your white one is the positive. They're all in series. You know, they're all sharing one leg at the time. So that means they're in series, right? So if I light this up, it's not gonna, like if I turn on my battery, it's not gonna work. It's not gonna light up, right? But if I change, let's say I connect this wire to here, these 2 are gonna light up. Or here, this one's gonna light up. Okay, anybody has any questions?
So you're saying, wait, all 3 of them wouldn't light up, or just like the last one wouldn't light up if you were
All
to
3
tap-
of them are not gonna light up.
Oh, okay.
Yeah, so if people had it light up, they might have used the red LED, right? If you had 3 red LEDs, there's a chance you might have lighted up, because I will actually explain it later, but because red color is what is it called? Has the lowest, what do we call this?
Voltage drop?
No. Red color is has the lowest lambda. What was it? Does
Wavelength?
anybody know? Yeah, wavelength, right. So it has the lowest wavelength.
Or-
So in order
yeah.
to jump electron to emit a light, you need less energy, right? So that's why if you had 3 red LEDs, you might have light up, right, in series still. But then if you go to blue, like making blue LED is really hard because it has a what is it, larger wavelength, so it's really hard
I-
to make it.
I think I meant to say frequency. That was my bad.
No, that's actually wavelength. Yeah,
Because red has like a really long wavelength. That's why it has low energy. Did I
right.
get
Yeah,
that? Oh,
yeah,
okay.
yeah. I think so. Yeah. But yeah, it just goes back to the color's wavelength, basically, right? The amount of energy you need to pop electron out of its place, then it goes back and then start emitting light, right? So there's a lot of good videos outside on YouTube and everything that you can watch about why making a blue LED is really hard. But yeah. Okay, so this is a top view. Again, they're in series, they're sharing, right? They're not gonna light up. I have this off, but they're not gonna light up, trust me. And then so I was reading the answers basically from everyone, like what is called form and everything. Some people had a really good analogy, which is a power, right? As you add more LED into your circuit, the consumption of the power is gonna go up, right? So if let's say if any LED wants 2 watts, right? When you add the 3 LED, it's gonna be you need 6 watts, but you can't really provide 6 watts to your circuit. So that's what is happening, right? And the second really good analogy is that when you add things in series, right, the resistance is gonna increase because it's a summation, right? So when the total resistance of your circuit is actually increasing again, your current is gonna go down. Anybody has any questions? Any questions?
So the second correct answer would be to put it in parallel.
Yes. I will go through it why, and then so any other questions? Any questions? Okay. So we go here. So again, now since I talked about power, right? Your power is basically V times I, right? The units for power is watts, which is basically joules per second, right? And your IV curve always talk about your power, right? So anytime that you have a voltage and a current, just really pay attention to the watts that you're kind of using, right? And that's how they measure a lot of like low power LEDs, right? Because you want to consume less power but being efficient. So efficiency also comes from power is basically the input power divided by output power or something. I don't remember, I don't have it here. But yeah, efficiency is also something that you need to kind of look when you're working with systems. And then, we can manipulate all the equation and we can get P is equal to V squared over R or P is equal I squared times R. So these are the other two formulas that you might want to use when you're calculating power, right? So the basic, let's say, we have a 10 volt battery and we want 2 amps to go through the circuit. We actually providing 20 watts to our circuit, which is 20 joules per second. So really important just conceptually to think about it. Typically, when you work with a power supply provides both voltage and ampere, and they all have a limitation on their wattage that they can provide to the circuit, right? So if you want something to run on 4 amps, you either use 5 volts, right, for 20 watt, right, or you need to bring down your ampere and turn up your voltage. So these are like some ups and downs that you need to think how you can kind of provide to your circuit. Anybody has any questions? Any questions? Okay. So now if you want to calculate basically if the LED was a resistor, right? So LEDs don't have internal resistance. So I said if you assume them as resistors, right? What's gonna be the resistance of them if you just think of them as resistors, right? Because we saw that the voltage was dropping and the current was dropping. So what is gonna be their resistance? What is really appropriate again to calculate is that based on the circuit we have and how many LEDs we have in the circuit and what orientation they are. So if you had two LEDs, their resistance would be about like 2,500 ohms, right? But when you had three LEDs, right, we can actually ignore the 220 ohm because the ampere is really low again, like it's order of 6, basically 10 to the power negative 6. So you can just ignore it, right? So 5 volts is basically 3 of the LEDs you have times the 25 micro amps, right? And then you just solve it and you're gonna end up with 69k ohms. Anybody has any questions?
So we can use Ohm's law just be viewed as like in terms of like the whole circuit.
Yeah, because the question is asking if we assume there are going to be resistors, right? In the third circuit, right? What is gonna be their resistance?
Okay.
Right? Because we can't really calculate LED's internal resistance, and it's because they're diodes, right? And later on, if you take any semiconductor classes, you're gonna see that the internal resistance is not even in the equation. So it's like doesn't exist basically. Any questions? Oh, I measured the value of the current for each part of the circuit, right? And then if you kind of put everything together, you're gonna end up with the same numbers, right? Because I think the minimum that you need to light up a LED is like you need 1 milliamp, like and 5 volts, right? So about what does it call? 5 milliwatts. But when you have order of like really low current, right? You know providing enough power to your LED so it's not gonna light up. If that makes sense. Anybody has any questions about this?
So the reason that 3 lights are not turning on is not because of the resistance. Actually,
Yeah, it's not because of the resistance, because they don't really have resistance. What is happening is that there's a voltage drop across them, right? So the reason I say use LT spice is that you can't really see the current through them because it's gonna be the same. Like it would show, I don't know, on the what is it called, 10 to the power of 9 current something, which is something you don't want to think, right? It's kind of the limitation of the software that we
Yeah.
have, right? So you need to think more thoroughly and see what tools you have, but it can actually measure the voltage kind of correct. So you can see there's like about 1 volt drop across each what is it called? Each LED,
okay.
right? So that's why when you have a really low voltage drop and the voltage is actually dropping all across them, right?
Yeah.
Then you're not providing enough power to any of them because the current also went down.
Okay.
Right? So then you're not providing enough power, so then they're not going to light up.
Yeah, makes sense.
Yeah. And then the solution was basically just put them in parallel, right? And does anybody know why we should have put them in parallel?
Because the resistance can, oh, I mean, we don't have the resistance, but
Current stays constant.
Hmm?
The current stays constant.
Actually in parallel the current changes, right?
so but the voltage drop's gonna be same for the lights, I think, because they are in parallel.
Right, yeah, because they are sharing one node here, right? So whatever the voltage drop is across these resistor, it's gonna be the same voltage they're gonna use, right? So in the end, the voltage drop is gonna be 0 here. So like, let's say if there's 2 volts drop here, they getting power from a 3 volt power supply. Like, if that makes sense. There's 3 volts here, so they can actually light up.
So, Sina, what you're saying is that the sum of the voltage will equal zero because of Kirchhoff's current law. Is that why?
Um, mm, I mean so if there's a 2 volts drop here, right? Across any of these what is it called? Any of these LEDs, right? There's 3 volts drop, right? So that means we are completing the circuit. So the total voltage drop is 5 volt in the circuit at each branch, right?
Okay, gotcha.
If that makes sense.
Yeah, yeah, it makes sense.
Okay, yeah. And because of like, you're sharing the same node here, which like, let's say 3 volts, then they can light up, right? Because you're providing enough power to all of them. So basically the purpose of this question was like, you guys think really truly in a what is a good question, right? Break it down, see what is wrong, and come up with the right solution. It was really interesting to me that some people actually wired their circuits wrong at first, and they had the LEDs light up, and it was like in parallel. I was like, okay, you kind of like, you have it lucky, if that makes sense, right? But it's good to read the questions right again, try to come up with a better solution, right? And then yeah, anybody has any question or anything about this question that they find interesting? Any comments? Anything, you guys?
When we put the LED lights parallel like that, we can just add as many as we want, and then as long as the circuit's closed, it doesn't matter. Like it will still light up.
Okay, so in the series circuit, right, the limitation wasn't really the current, was the voltage, right? We had a voltage drop across all of these that couldn't supply this last one. So the resistance would basically go high in the circuit, right? If there were resistors, right? Because the voltage drop. So there wasn't enough power going through this. So you would basically have a almost open circuit. Almost open circuit, right? But here in a parallel, right? What's gonna be our limitation if we add more LED? Anybody knows? Right, it's gonna be current. Do you know why?
Because the current split up for each LED.
Yeah, exactly. So, if the input current here, right, at these, like after that goes through the resistor is, let's say it's 1 amp, right, and you add 5 LEDs, right, then you're gonna have 0.2 milliamps, right, about that, right, 0.2, no, 0.2 amps, right, going through each LED, right? So now let's say we have 100 milliamps, right, and you add 5, so it's gonna be 0.2 milliamps. If you add 10, that's gonna be 0.1 milliamps, right? So that's how the current is going to divide across all of these, right? And after some time, you're going to have less current going through each end, so then they're going to light up because of the power you can provide to them. Make sense?
Yes, thank you.
Yeah. Anybody has any other questions? Any other questions about task 2? Any comments that or something you guys find interesting about this question if you want to share? Or something that you didn't know and you just learned? Just share it with us.
So yesterday when I put 2 in series, none of them lit up. I tried a bunch of things and it still didn't light up. Is it just because yeah, I still haven't figured out why, but I understand why it's like it works in parallel now.
Okay. Okay. Thanks for the feedback. I'm glad that you're gonna know now. Thanks. Anybody has any other things that they find interesting about this task before we move on? Okay. So, and this is the side view. So if you want to debug your circuit, you can go back to the pictures. I prefer to put the pictures because when I show my camera, it does really, it's not that visible. So I was like, it's better for me to get a better picture and just put it on the slide so you can see them. All right, so task 3 was basically lighting up using a potentiometer. So was a potential a new things for you guys to use? Just say yes or no. On the chat. Okay. Okay. So I hope you guys found it interesting. But if you want to kind of again, like break down the problem, what is the problem telling us in the first question? Can anybody explain? Can anybody explain that? What is the first question asking us? How can we go for it? Anybody? Okay. So the question tells us like when it's the brightest, right? The current is 25 milliamps, right? So what do we know about the circuit at this rate? Can someone explain, please?
Not a lot of resistance.
That also we can tell that we know they're in series, right? So the current going through both the potentiometer and the LED is the same, right? So we can just use Ohm's law again and divide the 5 volt that we have by the 25 milliamps. We're gonna get about 200 ohms. So at the lowest resistance, we had about 25 milliamps. It was the brightest, so it's 200 ohms. So what about when it's like 2 milliamps? What can we tell?
So it has like a high resistance.
Right, it has a high resistance. They're in series, right? And then we have 5 divided by 2 milliamps, which is gonna give us 2500 ohms. Anybody has any questions about it?
Why is it not zero when it's the brightest?
When is what? When is the brightest?
Yeah.
So think of it this way. Can we have zero resistance because the Ohm's law, right?
No,
Five,
I thought the question is asking about the resistance of the potentiometer.
right. The resistance can't be zero, right? Because
I mean,
again,
like the potentiometer is in series with the LED, but like LED can, you just said that it can be it can be deemed as a equivalence of resistance, right?
okay, so the LED is not a resistor, right? They don't have any internal resistance at all, right? They're diodes. And like when you take, if you want to take the, what is it called, semiconductor physics, you're gonna kind of realize that there's no resistance when you have a diode, right? And LEDs are basically light emitting diodes. But the questions that I had in task 2 was, if we assume that our LEDs are gonna be our resistors, what's gonna be their resistance, right? So I don't want you to confuse them or kind of see them as resistors. They're not resistors.
Right, thanks.
Yeah, yeah. They don't have any resistance, anything. The question was basically just assume them if there is resistance, right? So it was just a test to see how we can kind of analyze our circuit in a better way than just like, yeah. Oh, okay. So I actually had the same problem. I was just playing around with the potentiometer, right? And then it kind of popped. I think, what do you think would be the reason the LED popped?
There's too much current going into it.
Due to the power rating.
Yeah, power rating, too much current, right? Basically, right? And yeah, no resistor. Basically, like, the resistance was so small, about probably like 1 ohm or 5 ohm, 10 ohms. Like if you kind of Google the, what is it called, the potentiometer they have, like you can kind of see the limitation that from what resistance to what resistance it's going to cover, right? But the question was just basically how we can kind of measure it with the measurements we have, and kind of we can guess about the, what is it called, the range of resistance, right? So yeah, our numbers can be a little bit different from the things they might have on their website or when they sell it, right? Any other questions? Any questions that you guys might have?
If you have some time, could you show us how to measure the current using LT Spice? Like, do we use the same command as the one we did?
Oh, for the LEDs?
Yeah.
Yeah, I will show, but I think it is really hard for the LT Spice to measure the current through a LED. Again, it's because it doesn't have any resistance, right? So you might see the order of the magnitude of your current at about like 1 teraamps or something, which is really high, but that's not a true thing, right? So it kind of shows us our software limitations, but I actually have it ready, so I will go and do LT Spice after this. And then, yeah, I need to change this. The blue wire is connected to negative and positive, so I think I have it wrong here. But the orange wire is connected to the middle. So did anybody test what if we change the, what is it, from the left leg to the right leg? What's gonna happen?
It won't turn on.
Hmm?
I meant like it won't turn on because like it won't receive power. Is that why?
No. So
But
if
in
you
the
change the white wire, not the orange.
They're gonna flip because like the total resistance of both sides is the same. So they add up to be a certain number. So it's just gonna, let's say it starts from like the brightest to the dimmest, and then you flip it and it becomes dimmest to brightest.
Yeah, exactly, right. It kind of switches the direction of the resistance. Oh, so there was a question in the chat. They say in the diagram I showed. Yeah, so in the diagram I found on YouTube, because I just copy pasted it, but you didn't really need to have a 350 ohm. And if you paid attention to the diagram, it wasn't something that we were using, right? They had a 9-volt battery, but we only had a 5-volt power supply, right? So it would have been like, if you just maybe you thought about it a little bit more, you would be like, this is not the same thing that I have. But then, yeah.
I have a question.
Yes.
So does that mean that the range of a potentiometer doesn't start from zero? It wouldn't be that wouldn't be a little weird?
Yeah, so definitely it doesn't start from zero. And then it's because, like, I think the way that potentiometer works is based on where's the orientation of the voltage on it, right? So that's why when you switch your white wire, you're gonna have a different direction, right? That makes sense,
Mm-hmm. But like,
right?
why wouldn't it be like screwed to one side? So that means I mean, they just short circuit and become zero.
Yeah, so like you don't want to have zero resistance in your circuit again, right?
I see.
So even like, any manufacturer, right? And the material they use, it's really hard to have something that has zero resistance anyways, right? Even your copper wire, they have some really small internal resistance, right? But it's so small that you don't really count it.
Okay,
But when
thank
you
you.
have but when you have a really high, what is it called, like thick wires or like a lower AWG, if you know about the gauge, like a wire gauge, right? They like as you go down, they get thicker. So the reason it gets thicker is because they wanted to have more type of resistance when there's like short circuit, right, or high current going through, right? So you can control it better. So in the really like high power applications, they use really thick wires. If you have ever paid attention to that.
Yeah, that makes sense. Thank you.
Yeah. Yeah. So let's do some LT Spice per request. Do you guys want me to do LT Spice, everyone?
Yes,
For
please.
Yeah.
for dance
Yes.
too? Okay. I will do it. Alrighty. Share screen, LT Spice. Over here. Alright. So again, we press F2 over here. F2. We bring a battery. Right. And F2, we search for LED. Right. And then we can search for resistor. And then we make them the attic ground. Right. So and then if we run, actually I forgot my values. So 5 volts, 220, right? And then we run this for like 2 seconds. Right. So it shows that the current through this is about negative 19 amps, or basically 20 milliamps is going this way. LC space is a little bit weird again, right? And then here it shows it right. Okay, so there's about 20 milliamps going through our LED, right? And when we measure the voltage across this 220 is about 731 millivolts. So you kind of only need 1 volt, right, to maybe power this up, right? But the what is the role of this resistor here is to just control the current, right? Because if you have too much current going through this, you have so much power, right? Then it would just blow up, right? Again, power, right? And there's no internal resistance that can kind of prevent that. Any questions? Okay. So now I'll delete this and we're gonna make another one. We're gonna go 2 LEDs, right? We're gonna go 1 resistor. Gonna go battery again, right? I'm gonna wire them up. Go 5 volt. We go 220. Alrighty. So we can just close this. What am I missing? Ground. Right. And then we're gonna just run for 2 seconds. Okay. So here is kind of weird, right? But what we don't want to kind of look at is the current, right? In this application, right? But still, the first, it shows about like, what is it, 50 milliamps again, right? And then 50 milliamps. But what is the problem is the voltage. See, the voltage drops. And then here we have kind of the same amount and they kind of light up, right? Any question about this? Any question, guys?
How do you toggle between looking at the voltage and the current?
Sorry, just a little bit of issues. But anyways, it doesn't really, I don't think you can toggle, but a good practice to do is to over here, the net name, which is F4. You select the net name. Let's say we select A, B, come here, and we say, and we can just right click and change it. B, and we can just wire this up here. Right. So now we have nodes A and B in the circuit. Right, and then if you run it again, and I select this, it kind of shows VA and VB basically. Right. So the voltage at point B, right, is about 0.75 volts, right? And the A is basically about 1.5 volts, right? And the current that we're getting across, what is it called? The current across like ID2 is about, again, 16 milliamps, right? Here it shows negative 16 milliamps, but they're kind of the same because it's the same way. Did that help?
Yeah, thank you.
Yeah, so it's just a better practice to have the net names, right? Anybody has any other questions? Yeah. So this is the circuit I had, right? So up here I have label net name. You can also right click and then over here on your schematic, right click, draft label net, right? Which is F4. And you can say A, you put it here. And it lets me select the second one, but select it and just right click and just B. Right, I can just wire it up. Right, or you can just put it on the wire here, it doesn't matter really. Right? Did that help? Oh, okay, yes, but how can we see the current? Okay, so I run, right? So you can select on one of your components your loads, and then it shows if like kind of what is it, directional arrow. So you select it. I select the second one, and here for the resistor, it kind of shows onto the left. That's why you get a negative one. So you get like about negative 16 milliamps, but here's 16 milliamps. But so the actual thing is that when I measured with the ammeter, right, it was a lower milliamp. So sometimes I'm not sure if we can trust this data that is kind of showing us right now. And maybe it's because it sees these as not having an internal resistance, right? So because the value is kind of staying the same thing, right? And then if we go to the third, did it help tall again or no? Okay. And then we go to the third circuit. I just delete again. Sometimes it bugs out. And then F2 battery, F2 LED, 3, and then R, we put a resistor here. Just F3 and just wire up. Two 120 ohm at a 5 volts. And then we put the net names again. A, B, and C. Okay. In 2 seconds. So here it shows that the what is it called? The current is about 12 milliamps, right? But what is the voltage drop? See, we have a really low voltage, like really crazy voltage drop. But still, right, on the L2 spice, we can't really tell, right, if the LEDs are gonna light up or no, right? Because like it's not real. It's software, right? We kind of just use it to understand the concepts better sometimes, right? And what was really important here is power is equal VI, right? So the current is kind of the same, but here we're not going to provide enough power in the very end, right? So this one is not going to light up, and probably this can be a small, like, open circuit, right? But the actual measurement I made with the ammeter, right? They were like really low values, which kind of makes sense why they don't light up or you have a really dim LED. Anybody has any questions? Any questions? All good? Everyone? Was the explanation good enough for you guys? Yeah, for sure. Was the explanation good enough to kind of make sense why task 2 happens? Everyone, just please type yes or no if it was good enough. Okay. Alrighty. Okay. I appreciate you guys. And then let's just continue then, huh? Any other questions you might have about anything that we kind of discussed till now? Okay. All right. So now we're gonna go over node voltage analysis for today's activity. You guys can probably solve 2 of these problems, and then I still want to add one more problem as a task, which is a fun one. It's more on hand. So during the break, I will probably add it to the slides, right? And then I will probably give you guys again like 45 minutes or something to do the task and everything and just work together. But this time I want you guys to do it individually. Just heads up. Like submit it individually, but just work together. Okay, so no voltage analysis. The voltage analysis is something that if you're E major, you're probably going to use it all the time in most of your circuits classes, EC3, EC10, 110, all of those. So if this is a summer, if you have time, go study it really well. I would just touch upon this a little bit because I like to do more hands-on things. So I hope so it can be more fun for everyone. But the node voltage is basically all about we kind of see the circuit as a connection between components, right? That's what happens in any circuits, right? There's components that are connected and they all typically share some nodes together, right? Some point that they are sharing and they're kind of connected, right? So we call that a node, right? And then here it says that basically in electrical is a point that 2 or more circuit elements are kind of joined together, right? And then it has to be through a conductor. Like that's basically what is a node. And then so just 2 minutes, 3 minutes, how many nodes do we have here? Just type in the chat in 2 minutes when you have it done. In 2 minutes.
I think 5.
How many?
Got 5.
4, 5, how?
Wait, hold on. Okay, 4.
So I think there's actually 5 nodes, right?
Was the
So
bottom?
again, oh, unless I made a mistake here, if I made a mistake, I'm sorry guys, but so a node in electrical circuits is a point at which two or more circuit elements are joined together, right? And it has to be they're gonna join together. So I think it should be 4 nodes, and I made a mistake in my solution. I'll fix it. I just saw it right now. But yeah, so there's one node here, right? We have one node here. This is one node. I think I counted one here, which is wrong. These are the same nodes. Okay. So this is one node, one node, one node, and one node. So 4. I will fix my solutions, and I'm sorry guys. Okay. Yeah, I mean it happens. You know, sometimes I was doing this like at 1:30 a.m. yesterday. So, yeah, it's a little bit, tough. But
It's,
okay. Yes.
I didn't get why R4 is not that like the one that next to the R4.
This.
Yeah.
So a node is a connection between 2 or more circuits component, right? So here, R2 and R4 are getting connected through one wire, right? So this wire is basically a node here,
Okay.
right? So one node, 2, 3, and 4. Any other questions?
Sorry, I had a question.
Yes.
Why was the last one not actually correct? The corner one, the one at the bottom left.
Oh, okay. So why is not 5 and I had a 5? Okay, so if you pay attention, right, this wire, right, is connecting R1 to R3, also to R5, right? So there is like 3 resistors sharing one node here. So this is only one node. So this is kind of shared with this. It's the same thing, right? It's a one piece of wire. They all kind of sharing, right? If that makes sense. Okay. So should we move forward? Any other questions about this? Any confusion? Okay. So a loop in a circuit, right, is basically a closed loop at that a path that electric current can basically take, right? So how many loops do we have here? So people who say 2, why there's 2?
One loop between R1 and R3, like inside that block, and then
Right.
Another loop inside R2, R4, and R5, that block.
Right. But we actually have 3 loops, right? Because we have a bigger loop that is R1, R2, R4, R5 as well, right? So this. Sorry guys. I have a lot of complications today. Okay, so does this make sense why this is 3 loops? Okay. So yeah, 2 small loops and 1 big loop. Okay, any other questions you guys have about this? Any confusion, anything? Okay. So we're gonna get kind of into the fun part of the electrical engineering. These are like EC 102, 113, and other classes that you gonna go through as electrical engineer, or if you want to do E as your tech breath. So these are really fun topics. They're really fundamental to so many things like radio frequency to how your computer stores data. All of these is basically these signals and systems, things between analog signals and continuous value, like digital signals. So anybody knows what is an analog signal basically? And just come up with a example. What is an analog signal that we kind of See, what is the example for analog signal? Somebody unmute, please. Somebody. Okay, so basically analog signals, right, are continuous signals, right, that there's no cuts between them, right? Like for example, when I talk, right, my talking has an analog signal basically. It has a continuous frequency that continues like through air and it's gonna continue, right? But is the voice that you're kind of hearing and your computer processing, is it analog or is it digital? Right? Any other guesses?
Digital.
So, any other guesses before we're gonna discuss this? Right? Yeah. So, very interesting. What is good? When my microphone is basically hearing my voice, right, is transferring my analog signal to a digital, because then computers can only understand digital, right? Zero ones, right? So you have to compute it through that, right? Then it comes to your speaker and starts simulating an analog signal, right? So it's basically this guy here, right? So it's either 1 or 0, right? Or it can have some amplitude later on, right? But what we hear, because it's really fast and it's really close to each other, we can hear as analog, but it's still kind of digital, right? Because it's really fast on and off that happens with our speakers, if that makes sense, type of thing. I can be a little bit wrong because like, there's some different analogies, but just like keeping it simple, our computers, our microphone is basically getting analog signal and converting it into digital. Any question about that? Any questions? Okay. So again, we say real world is basically analog, right? We can represent analog signal as digital signals again, right? Does anybody know how we can represent any analog signal with a digital signal? What is the way that we're gonna do it? Anybody knows how we can convert any analog signal to digital?
It's not pulse width modulation.
Right? Yeah, we can take samples, right? We kind of sample, let's say, I have this original sound wave, right? And then I can sample it like, per, like, let's say 0.1 per second, right? So one sample per, I don't know, like 10 samples per second, right? Then later on, right, in electrical engineering classes and even in mechanical engineering, we have something called kind of like a Nyquist rate, which is really important to kind of converting any digital signals to analog again, right? And that's how any binary thing is really saved in your computer, right? So if you guys are interested in kind of knowing the background and the back end of any of these things, you can take EC 102 or 113. Okay. Okay, does anybody know what is impedance?
Inverse of resistance.
Inverse
Never
of
mind.
resistance?
Never mind. I think it's like
Resistance of like, electrical components, almost.
Basically, the resistance in the AC
like
signal.
equivalence of resistance. Like when you calculate it, you can use that to calculate the current voltage and other things.
Right. Like if I want to be really honest, impedance is kind of hard for me to understand as well, right? But basically, yeah, basically what we should kind of understand is a resistance in the AC world, right? So, and again, impedance is so in electrical engineering we're going to deal with a lot of uh imaginary numbers and complex numbers, right? So anything, right? Any number has an imaginary part, right? But real numbers, they just have the imaginary part as 0, right? So the impedance is there for us to kind of understand when we have a AC circuit, right? How it's going to behave, because any AC function, let's say cosine is a real function, right? But when you have a sine, it's actually imaginary, right? So you can't really explain it with ohms. You have to explain it with impedance, right? Any question with that? Any questions about impedance? Or do you have anything cool about impedance that you want to share? Okay, so again, impedance is basically a complex resistance, right? That has a real part which is resistance and imaginary part which is reactance, right? And it's measured in ohms, so it's basically the same thing, right? All right, so we can talk about impedance with z equals r plus jx. Does anybody know why we have j, not I?
Taking my current.
Yeah, basically, yeah, because in electrical engineering, I is basically your current, right? So we need to use J. Yeah, exactly. Yep. So we can so this is basically what's it called, pre-calculus, right? And the magnitude of any complex number is basically the real part time squared plus imaginary part squared under the square root. And then the phase angle is basically your arctan or tan -1, your sine over cosine, or which is your imaginary part over your real part, right? Any questions about this? Anybody has any questions about imaginary axis or anything like that? Because we're gonna see this a lot in electrical engineering and just like a lot of classes, especially in controls, signal systems. So any questions about this? Okay. And I think before we get to capacitors, it's good for us to kind of take a break, like 10 minutes something, and we come back. What do you guys think? Sounds good? Yeah. Okay, let's take like about 10 to 15 minutes break till we come back. All right, see you guys. So anybody can explain what is a capacitor? Any idea? Anything you have? Just share it with us. No judgment.
Like two oppositely charged plates that like group collect charges and create like an electric field to store energy.
Basically, yeah. Yeah. Anybody know what is capacitor's application?
Like to supply energy to the circuit when there's no like voltage, no like supply of energy itself.
Yeah, that's one of them. Any other ones?
To stop either AC or DC.
Okay. Someone said filters. Filters is one of the, yeah, helps reduce the noise. Yeah, it's one of the actually greatest, like, tools for us to reduce the noise, right? And in the industry, you will see a lot of low pass and high pass filters, right? Um, we would go through low pass and high pass filters probably tomorrow I really want to go through them, kind of maybe drive some equations for them and see what they are, why we use them. And then today just a basically introduction to capacitors, right? So yeah, capacitor is basically two plates, metal plates that they're kind of really close to each other, right? And there's a space between them. Typically, so it's some sort of a gas or any material. It can be something can be solid. Uh, and then they can behave as a voltage supply when there's no supply to our circuit, right? So you can charge them, and then when you take out the supply from them, they're gonna start discharging, right? Any question about this? Right. So yeah, that's the capacitors. And then anybody knows what is the impedance for a capacitor? Or do they have any impedance? Do they have resistors? Do they have any resistance or anything? Does anybody know?
No, it
Sorry, what's
doesn't.
the question again?
I just don't remember
Oh,
the equation.
oh yeah. What is the equation for capacitors impedance, or do they have impedance?
I remember it was X.
1/J omega C, I believe.
Right? Yeah. Yeah. Oh, you were gonna say something, Sherwin? Go ahead.
I was like, I forgot the formula, but I know it was like XC. So
Right? Yeah. X. Oh, and then before the thing we kind of got here over here that X was basically reactance, right?
yeah,
Right.
Mhm.
So and then Cat C said that if I'm saying your name right, that is negative J over what does it call J omega C. What is it omega C, right? So what does the omega tell us about the capacitor basically here? What is omega? Anybody knows?
Frequency.
Right. So what does it tell us about a capacitor and its behavior? Anybody knows? So let me just type down the question in the chat. It doesn't short low frequency. So let's say we have negative J1 over omega C, right? The W is basically omega here, okay? And omega, right, is 2 pi F, right? 2 pi times F. So anybody can come up with any analysis that what happens when we have a low frequency and a high frequency, what happens? So if you have, let's say, 1 omega, right? And so that means let's say you have 1 hertz, right? Your basically your equation is like negative J1 over C, right? So it doesn't really change anything. And if you have like 0.1, it just goes up, right? So if you have really, really low, like close to 0, it goes to infinity, right? But what happens if you have a really high frequency? Let's say like, what is it called? I don't know, 1,000 hertz, 2,000 hertz. Low impedance, right? So yeah, then it acts as a short, right? Then it acts as a short, right? And then it doesn't let the frequency to pass through, right? So it kind of acts as a low pass basically, right? It doesn't let the high frequency goes through your circuit. So it kind of prevents a noise that is high frequency into your circuit, right? So I think I really want to go through this topic. It's a fun one. It's interesting for electrical engineers. Probably tomorrow, right? So just like I'm trying to build you guys up, see if you can understand it, and then tomorrow we will go through that and then inductors, and probably MOSFETs, right? So the task today is going to be something that tomorrow, or when you learn Raspberry Pi, you can kind of implement it with your MOSFET. So it's going to be cool. Okay. And then again, so we have a usage of the capacitors, right? We can use them as filtering. They can, filter any noises basically. It depends on how you use them. They can either filter, it can be a low pass or a high pass filter. They can change the timing in your circuit because of their discharge or discharge and what is it called? Their transient part of the thing. And they can use be in coupling and decoupling part of your PCB, right? So I don't really know about coupling and decoupling. I just put it here so for your knowledge. But later on in a lot of PCB, when you see you have, I think when you see a lot of like capacitors next to the power supply that is going to your microcontroller, those are decoupling capacitors if I'm not making a mistake. If I'm not making a mistake. So if I'm making a mistake, just shout it out. Okay. So yeah. And then so we kind of realized in our discussion that the capacitors have an impedance, right? So they kind of can be resistors, right? And this is how we can add series capacitance and parallel capacitance, right? The series is basically series capacitance is basically parallel resistors, right? And parallel capacitance is basically series resistors, right? So you add when they're in parallel, you kind of add the reciprocal together to when they're in series. Any questions? All good? All right, so let's just take like 10 minutes for everyone to solve this. Right, and I haven't solved it either, so I'm gonna solve it too. I'm gonna check answers. Hopefully I don't make a mistake, and we're gonna kind of let's go do LT spice too. Okay. Sounds good to everyone. Just like 10 minutes to solve this. Use any method that is gonna easy for you to solve it, okay? And I would probably just do node voltage analysis because that's the easiest one. If you guys are okay, just say yes in the chat, please. Thank you. 10 minutes. All right. Okay, so very interesting because I did this problem before with the node voltage analysis, and this time I did a voltage divider, so they both work. The answers should be like 11.25, 15, and 3.75. I think that's what I got as well. Yeah. So can anybody tell what method they used?
I just I just collapsed everything and then I solved for I total after solving for R total. And then
Right?
I just kept working backwards.
Right. Yeah, that's one of the ways to do it. And okay, I see the voltage divider, K loop love for V3 mesh, right? I think LT Spice. Yeah, LT Spice is good. Yeah, I was gonna actually do LT Spice. I was like, I shouldn't give up because I didn't do this problem, right? But let me share my screen. And then I would do the voltage divider method. That's what I did right now. But then I would probably share a node voltage way also. Or maybe I would do a problem tomorrow for node voltage. Okay. I really wanted to at least solve one of those, but I've been just like, just be honest with you guys, I've been a little bit busy. So didn't really have time to do everything. So yeah, I'm sorry guys. Okay. But let's just do the voltage divider because voltage divider is really useful anyways in real life. So yeah. Okay. So can you guys see my screen and everything? Okay, so you guys tell me what is the first way for voltage divider? that I have to go here. What do we see? Any inspection that you guys have right away? Also, this. Any inspection that you guys have?
V3 is parallel to V source.
V3 is parallel to the V source, right? So what can we say about these node voltage?
Node A is 15.
Yeah, it's 15 volts, right? And what can we say about node B voltage?
Ground.
Hmm?
It's ground.
Yeah, it's 0 volts, right? So there's a lot of ways we can do and just break down the problem, right? One way to just, how can we actually, before I even explain, so how can we get to voltage C? What is VC here? What is
It's,
happening in the circuit?
It's just 0 plus Ri.
0 plus Ri?
Mm.
What do you mean?
We go up. Gotta add
Oh,
the.
I see. So you say the current goes up.
Oh, actually, there's,
I mean, if you want to do a what is called node voltage analysis, right? What we can do is that we can say this current goes here, this goes here, and this goes here, right? And we know that the current through series is gonna be the same. So one way to do this is to combine these two resistors, right? So go 200 and then here just draw it this way. So this one says 200, right? Oh, do have it. So what is this one? The resistance of this guy now,
400.
right? Okay. So now one thing that we're missing that by combining these two is that we can't say anything about node C voltage, right? So we can still solve this and maybe combine, like bring them back again, right? But it kind of kind of lose the data, right? So that's not what we want to happen, right? How can we get to voltage at node C? Anybody?
Uh, can we just solve for the whole current and then see how much current goes to that line, goes to that like the 400 one, and then this just the Ri of that.
Yeah, so one way that we can do, obviously, I think a lot of people do, is that we calculate the total resistance of the circuit, like the one that we did like last time, right? So these two are in parallel, right? So we can do this way, right? Divided by 400 plus 200, we get about, what does it go? 8,000 divided by, is it 8,000? No, no, this is right value. Divided by 600, right? So we get, what does it go? 8/6 times 10 to the power 2 ohms, right? And then we can calculate the I total, right? Which is 15 divided by that value, right? So this is 1, 5, 2, 4, 5/4 times 10 to the power 2. If I'm not wrong. Did you guys get the same current for here? For I total, this I.
That 9/80. I told.
Hmm?
That 9/80.
9/80. I'm probably just miscalculating it here. But yeah, so just going through it is that we can calculate the I total, right? And if we know what is I total, and if we had a equation like with the KCL, we could say, oh, I total is basically I1 plus I2, right? anything that enters a node exits a node, right? So IT is basically what is going to go in, and the I1 and I2 are something that is going to split, right? Yeah, the way I did it was I didn't really do the current, so I don't really know what is the right value for the current, right? The way I did it right now was the voltage divider. But what I'm trying to say that this way is also correct, right? As long as you make a good calculations. But what makes this way a little bit like harder to calculate is the numbers, right? We end up with like some like numbers that are not right for us, so it's gonna make it a little bit harder for us to calculate. One thing that I use and I found it really useful, right, was to use the voltage divider. What was the voltage divider formula, guys? What was the V out? It was equal to what?
Yeah, it equals Vn times like R2 over like R1 plus R2.
Right. Okay. So we can find voltage at node C using the voltage divider, right? So VC is basically 15 volts at node A, right? R2 is 300, right? And then divided by 300 plus 100, right? So which gives us, I think I do have, I don't have it, but what does it go? 15 times 300 divided by 400, right? 45 divided by 4, which is 11.25, I think, volts, right? So everyone basically got that. So the voltage at this node now is 11.25, right? It was like really fast calculation, and we actually find out our V2, right? 11.25 is our V2, right? Because like the voltage drop across 300 ohm resistor is basically 11.25 volts because here is 0, right? So with one step we find one of the values we wanted, right? Then now another really fast analysis we can have is that the 200, the voltage drop across the 200 is basically 0. Oh, what is it, 15 volts, right? So at 15 volt it goes to 0. So very easily we can say that V3 is 15, right? And then the last one is that we can use KVL on the understanding of it, which tells us the voltage drop across these two should be 0, right? Like this is a complete loop for us basically, right? So here I have 15 volts, here I have 11.25 volts. So 15 for V1, we're gonna have 15 minus 11.25, which is 3.75 volts, right? So with basically 3 steps, or just very like really only one every calculation, we could just get the answers, right? Anybody has any questions? Any questions? Everyone's doing good? Any questions why and how I did it? All good? If you did understand it, please just press I did. Or if you have questions, just direct message me. Just don't hesitate to ask questions, please. Okay. But yeah, just like saying it again, I think it's really important in circuit analysis, right, to choose the right method to get to the answer really quicker, right? Sometimes some ways would take you longer and they're gonna be heavier in calculations. So it's better to understand the really basic things in circuits before even attempting any problem. Like before I did so this I changed the numbers of this problem, but then before I did this in basically node voltage analysis, and it took me like about 12 lines. But with a small voltage divider, it can take you like 3 lines to just do the problem, right? So it's also important to be efficient and correct, right? And as you practice more with the basics, you can solve a circuit problem really easier. So as you get more experience, more practice, you become better. Okay, so if you can't really do this, it should be fine. You know, last year I think I was struggling these circuits too, actually. So, you know, it happens. Right, just practice. Any other question you guys might have? All good? Okay. So we are actually gonna go to break rooms now. There is 2 problems, right? You can solve them. Okay. So yeah, we're gonna go to break rooms, and then we have 4 type of tasks. There's like 2 problems that you have to solve. One of them is this one, right? You can do voltage dividers, anything you want to, just try to solve it. Use LT Spice to check your answers, right? And then this one is a find the equivalent capacitance of the circuit. So it's basically the same way as we did for the resistors last time, but I want you guys to do it for capacitors, right? And here now we're gonna do something hands-on, which is basically using button switches to make some logical functions, right? So the first one, we're gonna implement not function, right? And not function is basically when you press it, your LED is actually turn off, and when you're not pressing it, your LED is on. Okay. Any question about this?
Is your screen showing something?
Oh, okay. I am sorry, actually. Let me go over here. Okay, so in the break rooms, right? It's gonna be a small break rooms again. I want you guys to do it like together, but the form is gonna be this time individual. Okay, so I want you to just submit your answers. Nobody's gonna know. I will just see it myself, right? So, and it's just like for me to see where the class is, if I need to, and I'll probably put out like a feedback form, like just write whatever you want to, and then I'll probably listen, right? So, yeah. Yeah, the slide is actually on the website as well. So, and tomorrow I will go over these problems. I didn't really have time to solve them yet, right? But tomorrow I'll go through them again, like what I did today, right? And we can have a discussion. I really want you guys to work together because this way you get, when you work together, the understanding is going to be really better than just like solving it alone or just like watching internet. It's good to have a discussion.
Is that a 9?
Okay. Hmm?
That's supposed to be a 9.
What do you mean?
The voltage.
The Google form?
It is a 9. It is a 9. See, he's just talking about the voltage.
Oh, okay, yeah, it's 9 volts. Yeah, I'm sorry. Yeah, thank you, Ryan. But yeah, so I say use at least 2 method. Try to do 2 method, either KVL, voltage divider, combining resistors and just like going back. Whatever you feel comfortable, just get practice, right? And this one is the equivalent capacitance of the circuit. Is basically the same thing as your resistors that we did last time, but this time is for capacitors because the formula was different. If you remember, like in parallel, we add them together, and if they're in series, we add the reciprocals, right? So it's reciprocal of reciprocals. So it's a little bit different. But the fun one is going to be this hands-on one. So I want you guys to make a not function, right? A not function is basically when you press your switch, right? It's going to turn off your LED. When you take it off, it's going to be on. Okay. So think of it how you're going to wire your circuit, and you're going to have this truth function to happen. You probably would only need one switch and one LED. Oh, I would put the form when you guys come back. Okay, so don't leave the meeting. Okay. Any question about the not function that you want to implement? Anybody has any questions?
How are we submitting task 4?
Haven't thought about it, but in the end you're gonna see a form, so you can
Okay.
probably submit it. Yeah. Okay. And then we have a second task for, right? I want you guys to make AND function, right? So the AND function is basically, only is one when they're both pressed, right? And if you press the other one or the other one, they're both 0, you don't see any LED light up. So you probably need 2 switches and 1 LED, right? Use your concepts of circuits and everything to somehow wire this up and get this. I would make a, what is it called? A fifth task for whoever finishes to make a NAND function. A NAND function is a complement to AND, right? And I'll add this slide again. So if you want to go back to it really quick. So it's a complement to this function. So if any of them is 0, it's going to turn on. If they're both on, they're both 1, it's not going to turn on. Okay, so that's a NAND function, right? Any question you have?
Do you mind repeat that?
Okay, so you want to do AND function first, and if you have time and you want to practice more, do a NAND function. Okay, complement to your AND function. So that means if any of them is pressed, it's gonna be on, or if they're both 0, it's gonna be on, right? But if they're both pressed, it's not gonna be on. It's a complement to this. I'm gonna add
Right,
this slide
thank
really
you.
quick, okay? So you can go back to it. And then this is how you basically plug in your switch, right? This is the best way to do it. And if you can see my cursor, is that these two, right, are gonna connect to these two. Okay, so these two are connected basically together. So if you put something here, put something here, they're connected, right? But if you put something here and something here, they're not connected. And you have to press it to make a connection. Any questions? Any question about this before we go? You guys feel comfortable about doing this? Okay. So I'm gonna make the break rooms. I think I can. Right. I want about like 4 to 5 participants per room. Okay, so help each other, right? And then submit the form in the end. Any question before I put you guys into a room? Any questions? Any
How
comments?
does the switch work again?
Okay, so can you see my cursor?
Yeah.
Okay, so these two, right? These two over here are connected, and these two are connected together. So there is a wire basically here and wire here, right? But these two are not connected, if that makes sense, right?
And
So
when you press it, they just become connected.
yeah, exactly. So when you press it, these line is going to connect to this line.
I see, that
Okay.
makes sense. Thank you.
Yeah. So basically, when you're not pressing it, it is a 0. When you press it, it's a 1 for our convention, right? For some other conventions, for other switches, they can be normally closed, which means if you press it, it's going to open it, right? So depends, right? But for our case, it's this one. Any questions you guys might have? All good? Okay. So I'm gonna open all the rooms. You guys have probably about 45 minutes, okay?